Donc, merci Gabriel pour l'introduction. Et juste pour l'information, la présentation sera en anglais, mais vous êtes libre de poser vos questions en français. As an introduction for our study, I know we need to reintroduce standing column wells again, since our study focused mainly on this type of geothermal heat exchange system. They are considered an efficient system since they take benefit from several heat transfer mechanisms, such as here the conduction in the rock and fluid, convection between the borehole and the fluid, and advection due to groundwater flow. And these systems are also considered cost-efficient systems since they provide the better thermal output for shorter borehole length compared to their closed-loop counterparts. However, during the normal operation of standing column well, we don't need an injection well, meaning groundwater is pumped here from the main well to the heat exchange system and then returned to the main well. But during the operation of what we call bleed, in that case, we need an injection well, meaning that part of the water will return to the main well, while the rest is redirected to an injection well. This bleed procedure will create a local hydraulic gradient between the injection well and the standing column well, which will increase the advective heat transfer. Also, several studies have proven that this bleed operation can decrease the required borehole depth of a standing column well, and also it prevents the standing column well from nearby freezing risks. However, using injection well for bleed has its own downsides. Like, for example, there is the issue of clogging due to the long-term operation of injection wells. Also, there is the risk of overflow, as shown in this picture here, due to the large bleed volumes. And we shouldn't forget the risk of thermal interference between the injection well and standing column well. Well, it doesn't happen most of the time, but if the system is not well designed or spaced, risk of thermal interference can be a serious issue. So in this case, our study aims to solve these issues and tries to find a new alternative way for bleed water disposal. So our proposed solution includes having infiltration as an alternative to injection well, and also using storage tank for the storage of large bleed volume. So this solution is illustrated in an underground perforated storage tank, meaning that rather than directing the bleed water into an injection well, it will be directed into a storage tank, and then it will be infiltrated to the unsaturated zone through its bottom perforation. And the site which is proposed to integrate this new bleed method is located, it's our experimental site located in Varennes, which is about 30 kilometers far from Montreal. In that site, we have an operating standing column well and an injection well connected to our mobile geothermal laboratory. And the hydrogeological and geothermal properties of this site are used for our methodology, and also the bleed parameters of the operating standing column well in this experimental site. Well, to prove this new bleed method, a finite element numerical model has been constructed for this purpose using COMSOL multiphysics. The purpose of this 3D numerical model is to predict the thermal and hydraulic behavior of bleed water inside the storage tank, and also when it is infiltrated towards the saturated zone. This numerical model, for example, in case will solve this kind of differential equations. Like, for example, in the storage tank, the fluid flow is governed by Navier-Stokes equation. In the unsaturated zone, it is governed by Richard's equation. And in the saturated zone, the fluid flow is governed by Darcy's law. And to represent the operational conditions of this storage tank in the experimental site of Varennes, these boundary conditions were implemented. For example, at the top of the model, we have included the effect of climate condition. In the sides of the model, we have included the effect of regional hydraulic gradient. And in the bottom of the model, we have included the geothermal flux considering the specific experimental site. And here the bleed water parameters, the bleed water when it is entering the inlet pipe of the storage tank were also included, and the parameters are shown in more detail in the next slide. So here, the bleed parameters for the operating standing column well are the bleed flow rate and the bleed temperature. These parameters are from the operating standing column well. It operates in 30-day period during heating mode. So what happens in this simulation period? This standing column well has generated about 120 cubic meter of bleed water to satisfy, to fulfill the heating demand of 6,400 kilowatt hour. So to investigate the performance of this underground storage tank, we propose to install a storage tank capacity of 20 cubic meter, meaning that the maximum stored water level, considering this design, is about 1.9 meters. So when we monitored the stored water level during the simulation period, we can see, like here shown in the blue line, which is the three-dimensional case, that it was half full, the storage tank, meaning that it was able to drain and store all the bleed water for this operation period. It was also interesting to compare this three-dimensional case with a similar two-dimensional case, and it is evident that the two-dimensional case somehow underestimates the drainage performance of the storage tank, because it's logical, since the 3D numerical model captures all the complete fluid flow compared to the two-dimensional case, where the drainage and the fluid flow is not complete. And to investigate the hydraulic simulation results, you can see here on the left side the pressure distribution inside the storage tank. It is interesting to see that during the simulation period, the pressure distribution follows the hydrostatic pressure gradient, which proves that our simulation predicted this pressure correctly inside the storage tank. And on the right side, we can see the saturation plot. It is seen that after 30 days of infiltration and drainage, there is a formation of an injection cone surrounding the storage tank, which is, of course, expected during drainage condition. And also there is a low possibility of overflow, because if overflow happens, means that this bleed method is not successful. And also, it's important to mention that the key element of this work is to couple Navier-Stokes equation with the unsaturated flow equation, or Richards equation, to mimic the drainage condition for this simulation. And it's also interesting to evaluate the drainage flow path, like we can see here, like the streamlines of the infiltration of the infiltrated bleed water reached the depth of fractured rock, and also it has rejoined here the existing, like here in the blue streamlines, the water which is due to the regional hydraulic gradient. And here I suppose that this results answer all the questions related to the groundwater sustainability issues for this new bleed method. And lastly, for the thermal simulation results, we have fixed the initial temperature at 9.4 degrees Celsius. And the thermal plume, we can see that here, and the thermal plume has reached a limited extent, meaning that there is a low possibility of thermal interference compared to injection wells, since the thermal interference of injection wells is much more deeper than the case of infiltration. So the contribution of this study, that we have proven that in specifically the underground storage tank is an alternative for injection well, but more generally that infiltration can be an effective method for replacing the injection well during a monthly period of bleed. Also, this storage tank, even though it's 20 cubic meter capacity, it has successfully drained and stored about 120 cubic meter of bleed water. And also, it's evident that using infiltration to the surface could lower the risk of thermal interference compared to injection well. But what could we suggest concerning this this work? That we can develop an experimental site to validate these numerical results, and also additional improvement can be implemented to model the fracture flow in the specific experimental site, since we have used the equivalent porous medium method to simulate the fracture flow. So this is the end of presentation. Thank you for your attention. Et je suis heureux de vous répondre à vos questions.